quite a full day in the little early because it's Friday, but a nice day of talks. And our first talk will be given by Emina Soljanin from Rutgers. For those of you who've seen Emina's talks before, you know that they're always interesting. There's always something nice. So I'm looking forward to this. Please take it away, Emina.
Thank you very much, Henry. All the organizers of the workshop, of the special semester at Simons, and all the speakers from whom I learned so much this week. So it's a mouthful, a little bit, my title, so let me not read it for you. And this morning I was debating, still until this morning, whether to first tell you what the application is, or until I still have your attention, tell you about the problem, but because it's fairly mathematical. But then I figure out, no matter how you turn it, it's Friday. So instead of you wandering through my math slides how she cooked up this problem, I'll tell you what it is about. It's something we worked on during the pandemic. So except for a few math conferences, I did not really have a chance to talk about it. So I'm going to look into distributed service system in where I have n nodes. And then I have concurrent users. So underlined here or emphasized in some way in text are usually words or scenarios that you haven't seen before. So it's not, I haven't seen before in related papers, say. And related things are LRC codes, batch codes, stragglers, etc. So there are concurrent users, so multiple users, and they are providing some service. It may be streaming, download. It can be storage layer of a computing system where multiple applications, meaning multiple programs, need to get data. And then we distinguish between two functional components. Again, there is not only storage, but there is service. So storage is a fairly standard model. We have k equal size data objects, and data object is, for this community, an element of a field. For a systems community with whom I collaborate too is often a file or something like that. And coded objects are linear combinations of these data objects. And each server stores only one for the talk today. So data objects can be recovered, of course, from multiple servers. And this type of things is often the easiest to illustrate on a simplex code. So here is 7.3 code. You have objects A, B, C, a little bit drawn differently so that I can nicely draw these servers, groups of servers from where I can extract A. So there are 4 for A, 1 systematic and 2 and 3 more that are 2 server objects. But now I'm going to introduce something that we don't usually pay attention to, and that is the service. So these servers are not something infinite, right, with infinite capacity. There are either queues, and they can finish jobs at some rate mu, or we can think about bandwidth of a server, which can simultaneously accommodate some mu users. Mathematically, they turn out to be identical, these two models. So this is how the service is. So multiple users can simultaneously access the service, but there are some capacity bounds connected to each server. Now requests for object I come at some, if it's a queuing model, they come at some rate lambda I. If this is only one server, you need lambda I to be smaller than ui in order to not to have the queues grow infinitely. And if it's a bandwidth model, again, you cannot pack more than mu users there. So your lambda I would have to be mu I. If there are multiple, they have to share this. And this talk is all about multiple things. So putting this now all together, I have 7 servers here. Oh, sorry.
You said on the previous slide that these two models are the same, but it looks like on the right-hand side, you have lambdas being naturally reals, and on the left-hand side, integers. Doesn't that make a difference?
That's a good point. With integers, we would like to, and that would be some, instead of straight lines, kind of staircase, yeah. But fundamentally, except for these conditions, they are identical. But excellent point, and thanks for So 7 servers and 7 queues. And now someone wants lambda A. So what I can do is split this request. I just put queuing because it's easier to draw. And for some people, maybe not for this community, real numbers are easier. Yeah, I guess who said that? God created integers, right? God created everything else is the work of man. So lambda A is split into lambda A1, A2, A3, and A4. So that this we call allocation. Right? Okay, and so my talk is about which requests vectors lambda A, B, and C I can serve from here, but not for a simplex code and but for MDS codes. Right? For simplex codes, actually, we also have a solution. But in general, one of the question is given a code, what kind of requests can you serve simultaneously? And here is again the formulation that I just said. You have these objects stored by a code. It doesn't have to be code the way we know it. It can be replication. In fact, there are advantages to replicating some. And there are some objectives. The one that I will address today, and this is determined in this set of lambdas, if a storage scheme is given. And there are others. What we like to do as coding theorists is design codes. So design a redundancy scheme if I tell you what I want to be served. And another is evaluate system performance. And that's this straggling community is working on. Once when you have this setup, what are the service expected times, probability that you won't get served, etc. So I'll spend some time here and then give you this as examples. Yeah. Any questions about the model? Okay. So I said that I gave this talk to math audiences, so I tried kind of to remove some of these more mathematical references and didn't completely succeed. So for example, here I'm talking about an arc, whereas it's an MDS code. So when you see this sign, this little ghost is ghost from the coding theory, right? But for us, it's not a ghost. So the storage scheme is defined by a matrix. It can be a generator matrix of a code. For me, in this talk, that's going to be. But it's in general going to be a multi-set of some points in some vector space. And since I'm going to only worry about linear independence, I can get a projective space. But for this talk, I'm going to focus on Reed-Solomon codes. And here are 2 Reed-Solomon codes. And coding theorists will say, well, the same minimum distance there, the same, right? Identical. From this service point of view, they're not. From a service point of view, they're not, and that is what this talk is actually about. Oh. So recovery sets, many people familiar with that in the audience, is just a collection of columns in G, in this collection of vectors in G, so that Ej is in their span. And this is, I want also that to be in some sense minimal, so I don't want there to exist any subset of that R, from which I can also recover this Ej. So in that sense, it's minimal. Unlike various other distributed storage scenarios, I am not going to insist of these recovery sets being disjoint either for one Ej or for multiple Ejs. So for example, here I have, for our matrix over there, I can recover E1 and E2. E1 is these, Ejs are standard basis vectors. So E1 is 1, 0, E2 is 0, 1. And then they have each further recovery sets. And if you see, for example, this one, 1, 1, and 1 alpha, 1, 1, and 1 alpha, they're in both groups. So the entire recovery sets are identical, and they also can overlap. So here I'm accessing this server, and I'm also accessing that server over there. So I disposed from many constraints that you have in LRC and other codes. And to address this problem of finding how many of these E1 and Ej I can recover simultaneously, not how many recovery groups I have for one or for other disjoint, but how many I can recover recover all of them simultaneously, I am going to use some notions in graph theory. Now, some of my former students prefer to work in geometry. For example, we worked with Alex Princeton student who was at Texas A&M, who also worked, like Nadia, who also worked with Krishna, etc. She loved geometry. To a certain extent, these are equivalent. So I told you about a matrix, nothing new for us here, except that it's not just generate a matrix of a code, but it can also have some repeated columns, whether they're systematic or not. And for that generator matrix, I'm going to define a graph. Some of the things that I'm defining here are universal no matter what these matrices are. At some point, some claims are going to hold, at least for now, only for MDS codes. Okay. So, yes.
Let's say if I take E1, and let's say a request comes in for E1, you will, the way to think about it is split into 4 requests, some portion going to the first. But if one basis vector is appearing in both sets, then those are considered distinct portions.
Can you point here what you mean?
If I look at 0, 1, for example, right? 0, 1 appears in the second set. No, in E1, I'm sorry, the recovery set for E1. It appears in the second and the third. So if you're splitting the E1 request into 4 parts, then the machine will dedicate one portion to the 0, 1, 1, 1 part.
Exactly. It may be a different user. I may be accessing this group, and you may be accessing this. And yes, the machine has to accommodate us both. Okay. Was that the question?
Yeah.
Okay.
So assuming that that machine can operate at that level of granularity.
Exactly. I have to have that constraint. Yes. That level of granularity. Was the question that we just had. Sorry, Aitan.
Is there a reason to do it for MDS codes? Because usually MDS codes are not the optimal codes for this type of.
No, it's not a reason. So the what is it called? We have results for simplex codes, and then since there were some connections with geometry, we thought, MDS would be interesting from mathematical theoretical point of view. Reed-Muller would be interesting there. We have only some partial results. Absolutely, there is no way. But one direction, as I said, take storage schemes we know. For example, I don't know, pyramid codes, LRCs, etc. Find these regions for them. So that's one direction. Another is someone gives you a region, find the codes for that. So there is absolutely, I'm not claiming any optimality here or particular interest of MDS codes, but it's something we are most familiar with, and we want to test our logic because it's a new problem.
But is it possible to phrase it as an optimization problem in the sense of I want to work with this rate? What is the best code that gives me, I don't know if it's the best region?
It's an optimization problem, yes. And you're going to see it in this talk as graph optimization, which are matching problems, actually fractional matching problems, which are LP problems. And it's a general LP for this. Yes, it's an optimization problem.
Thanks.
Anything else? Yeah, you want to pack something, right? Optimization. Okay. So now I'm going based on these matrices to define a graph. And then I'll formulate the problem. So how am I going to define a graph? For each of these columns, I'm going to have a node. And for each of the repair groups, I'm going to have an edge. So it's not a graph, it's a hypergraph, right? Because these groups don't have to be only size 2, but can be larger. So this is what it says here, and this is an example, right? There are 2 more nodes that I need. So for each, in this matrix, for each of the columns, I have a node. And then I have these 2 nodes. I need this for my optimization problem, which corresponds to the systematic. Why? That corresponds to these repair groups, which are just by themselves. So I want to give them an edge too, to be able to include them in the optimization problem. And so this is how this graph is going to look like for that particular matrix. So for each...
For this, or you can just do it with one node, the 0, 0.
So this is how I'm doing it. This is, again, a new problem. By all means, if anyone can improve anything, go ahead. Yeah. Okay. So and you can use it also solve it in some of these problems geometrically. Okay, so here we have a set of matrices that I want to consider in this talk. One is just the normal rational curves. Just Reed-Solomon, I'm going to refer to this G0. 0 means 0 systematic columns, and also canonical, Reed-Solomon, etc. Here is Reed-Solomon codes where I have replaced the first so many with the systematic columns, the first I. And I can go up to K. After that is not MDS anymore. Right. So for this talk, this is going to be my objects of interest. So graphs for this are hypergraphs, and each edge has at least at either size 2. These are those systematic edges we just discussed here with Dayton. Either size 2 or size K. It's a hyper edge of size K. Edges for me, hyper edges are going to be subsets of nodes. So cardinality of an edge is the number of nodes it contains. Again, to recap the definition of a hypergraph, V is a finite set of vertices that correspond to my nodes, plus the systematic addendums. And then E is a multi-set of V called edges. This is for general hypergraph. So graphs with parallel edges are hypergraphs, right? Because I allow a multi-set. So this is in general. For this talk, I am interested in something called quasi-uniform hypergraph. We gave it a name. There is a K-uniform hypergraphs, and those are those where each edge has the same cardinality. So regular graphs are 2 uniform hypergraphs, right? Because each edge has 2 nodes. And Km is each edge has either K or M cardinality. And in my case, they're going to be either, M is going to be 2. So they're K2 quasi-uniform. Example, if I have this canonical one, G0, it's a graph. Again, I cannot draw hypergraphs, so this is going to be examples. Each node is connected by 2 edges, so this is also complete. So this one is much easier to deal with in terms of matching, which are going to come later. And then this one has only E1. And then finally, the systematic has 2 additional edges. And because of the minimality, I don't have E1 anymore here. I only have E2, because if I had E1 here, this set 1, 0, and 1 alpha squared is not minimal for E1. So this is the graphs. One thing that is important to notice here is that each edge, I have put a label on it that corresponds to, so that corresponds to what I can recover minimally from the nodes that E includes. And notice that that partitions my set of edges, right? There are subsets of nodes where I can recover both, but then I have 2 edges, and they will compete for, that was Aditya asking, they will compete for the resources here. So my edges on this kind of graphs either have a label E1 or E2, and in general would be EK. So E is, again, the standard basis vector that lies in this K-dimensional subspace. Just to remind you, here, going back to Aditya's question, they're competing for resources. So these are nodes, these are disks. They're servers with a given capacity. And therefore, that kind of reminds you on matching and covering problems, right, in graphs. But I'm going to define what they are. What's a fractional matching? You can define it being a function or various things. For me, it's good to call it a vector. So it's a vector. The number of components in that vector is the number of edges. So now for each edge, I'm going to put a weight W. In a way that at each node, these weights have to sum to something that's smaller than 1. Otherwise, that server cannot serve that request. So if I have a fractional matching, I will be able to serve the request. And so for a recovery graph, we will also define something we call service rate for EJ, is when I now, since I have partitioned my graph into edges based on what you can recover, if I now sum all labels that are at E1, all weights in the matching that are on E1, I know that I can that's something that I can serve because it satisfies matching constraint. And here is one possibility. So lambda 1 is 2.5 and lambda 2 is 0. So I have these two objects that I want to get. E1 and E2 are the vectors. And if I, in this graph, have a particular matching, which is here, I can have this service. Why? How? Here I'm going to get 1. These are all zeros, then a 0.5 and 0.5 and 0.5. So 1.5 and I put 0 for the other. So that's how I'm going to. So out of this vector, which has W components, I'm going to get all components which are labeled by E1, sum their values. This is my service for lambda 1 and so on. So then I have all service rates. Are there any questions here? Okay. So question is, can we characterize the set of all these service vectors? And it looks a little bit daunting when you just first mention it, because this is essentially asking not solve a linear program which has exponentially many constraints, but find the entire polytope, right? And fractional matching is a polytope, and this service rate region is also polytope, and they're both convex, right? So now I'm looking for all matching of this class of graphs. But it turns out that I can actually get some answers, although it looks like, what are you talking about, right? So in general, matching problems for hypergraphs, these are fractional, so it's not integer, but they're harder than for graphs. They're different complexity classes. Okay, and just to tell you one more thing is that if I have, this is many-to-one map, so many different matchings will give me the same service point. So for example, if I consider here two matchings, which are 1.5, I want to recover the first, and 0.75 the second, what I'm going to do is, in this one, I call it greedy matching, and that's actually important for us. Greedy just means that I first load as much as I can systematic nodes. So I have here 1, here 0.5, I'm done with 1.5, and here 0.75. And then this other distribution of weights on this graph will give me the same point, but it's a different matching. So they're different. So it looks in the beginning, oh my God, what is this? But actually, yeah, this is a joint work with my student, Honglu Min. His name was written on the first page, and he has just joined last year, and this was the first paper we worked on together. So we want to characterize this matching polytope. What does it mean to characterize the matching polytope? Well, textbooks will tell you either determine the vertices of the polytope or give me the hyperplanes whose intersection is the polytope. So I can do one or the other. And sometimes it's convenient one and sometimes the other. And I'm not going to get into details about these things, but just to tell you principles that we are doing. And it turns out that, so for example, this will tell you what I can serve with that graph. So what I can serve is, if there is no lambda 1, I can go with lambda 2 up to 2.5. So I don't know if people see that. So one lambda 1 I can serve from here. And then you would say, if you're doing LRCs, I said, well, the other I can serve from here, that's 2. Where is 0.5 coming from? But I can split, because this is fractions. I can take half from here, half from here, half from here, and make 3 halves, actually. So I can serve 2.5. This line here, I can get from, so these points here, I can get from matching numbers, not the entire polytope of the corresponding graph. And this subgraph of gamma g induced by the edges that carry E1, And this number here, I can get by the matching number of this. Matching number is the size of the maximum matching. What is that? I sum all weights in that graph. Right. And so let's see. So some of these things are not hard to prove. So if I have this canonical Reed-Solomon code, then the hypergraph that corresponds to it is K-uniform, and it's also complete. If it's just K-uniform, some super smart people worked on that. It's problem of Erdos. There is a paper of Nogalon and a few friends, etc. So it's not that all K-uniform are well understood, but the complete ones are not hard. And so this simplex, which is lambda greater than 0 and sum of lambda smaller than n over k, is this polytope, this service region. Yes.
So when it comes to the code design, what is the objective? I mean, you want to get...
I am not talking about the code design yet. I'll come to that in a few minutes.
But
Here I'm given a talk.
But in a way, I'm guessing you don't want to use a non-systematic NDS code. It's better to have the systematic one in terms of optimization.
You are completely right, but it's not the topic of the talk, right? It will be mentioned at the end. Right. In fact, you want to prove that, right? You want to prove that systematic is not the best thing that you can do. Although it's kind of a common sense, that's why we have this greedy matching, still requires a proof how do these things scale. And interestingly enough, just by determining some simplex objects for these polytopes, you can make such claims. So for the polytope for the code that I just talked about, this one is systematic, right? The systematic for2 code, I have this red line. I know, and I can generalize that not from this example to general case, that this thing here, maximal achievable simplex, I can find. And I can find something that I call here, sorry, this is maximal achievable inside, and maximal matching is the outer one. And if I had here, what would be our LRC? A point here and a point here. So just by looking into not the entire region, but just by looking at these polytopes, I can make an inclusion relation like this. So this is your systematic, which has the smallest region. And then there is a how is this called? Strict inclusion. And I don't need to find the polytope. I can just find this matching, the simplices. So systematic, in this case, has this, and it starts to grow slowly if I remove systematic nodes. And if you notice, this thing, this 2.5 here is included into 2.5 to 0.5. It's a matching simplex. So matching simplex of these is going to be equal to the achievable simplex of that. So that is what's going on. So by just that reasoning, like it looked hard if you want to formally prove, of course, but you can do that by just looking at this simplex, which still requires, of course, doing some matching. Now, for other things, I'm not going to be telling you how we prove other things, but what do we use? We use the matching bound, which basically says if I sum a matching constraint to be smaller than 1 at each node over all nodes, I get the sum that is smaller than the number of nodes. And this is called matching bound. The matchings that satisfy this are called perfect. And when k is smaller than 2n, n is the length of the code, then we can find these perfect matchings in a fairly straightforward way. Also, another thing that we can show is the following. If there is a matching that gives you a certain service, then there is also what we call the greedy matching that gives you the same service point. And that greedy matching is the one that kind of favor systematic nodes. Again, something that you would think, yeah, it should be, an engineer would say obvious, right? Or, but then it requires proof. When k is smaller than n, when k is larger than 2n, things become different, right? So this is another way to visualize. Let's say my servers are buckets where I can pack these various requests, right? So lambda 1 is here greater than 1, so I will definitely get the first server systematic for it, part of this for lambda 2, part for lambda 3, and then later I'll do something which I said, let me not go into details, but it's fairly straightforward. And get constraints for these. And these polytopes for 6.3 look like this. So there is the simplex, there is something starts protruding as you introduce more nodes, more systematic nodes, until finally you get this kind of what we call it a turtle polytope. So Alton Kilic from Eindhoven, a student of Alberto Ravagnani, calls it a turtle. So this is the turtle polytope, so it's not straggler, Ravat. So now, suppose I change this 6 into 12. How is this going to look like? Actually identical, except that you are kind of flattening. This turtle becomes flatter, right? Now, what about when you get systematic nodes, the remaining non-systematic nodes become smaller than k, right? Things change a little bit. You cannot do this. This previous one looked a little bit like water filling, right? And here, it doesn't look like water filling anymore. In fact, it depends what you do. You may not have a perfect matching, that's what it says. But if you do something what you were doing before, you hit a wall at some point. You cannot recover 3 out of 2 in an MDS code. If you do it something differently, you do better, but still you have some capacity that you did not use. So for this type of codes, it's a little bit different. And it's interesting that, for example, when you have 2k minus 1k code, then you have this big flat service. If you have k plus 1k code, like 4.3 here, you always have this point, right? That can be shown. So anyway, we were starting to look into these polytopes, and some general work on polytopes of this service problem has been done by, in Alberto Ravagnani group by Alton Kilic, and then Janira Alfarano was a postdoc at some point. So they looked into what they can say about these polytopes, not necessarily MDS. So now here, I want to tell you a few before I end, just give you a couple of examples about these two. What Hashem was asking was design, and then there is performance evaluation. This would be stragglers people. Are there any questions about the previous? We can, of course, I'm here the whole day.
For the simplest case, where the sum rate is more than the endpoints, can you just explain the?
Is it? I'm going slowly. For 2Ks.
Yeah, just want to understand what it means.
This one. Yeah, I was debating whether to take. You mean how I get the red points?
The maximum sum rate edge.
The maximum sum rate I get to be 3, and that is because the vertex, the fractional lambda. So the maximum sum rate when I sum over all lambdas is the same as summing over all w's, because lambdas just collect a few w's at a time. Summing all vertex. Summing sum of weights in a matching, it's called the matching size. That is always smaller than something called vertex cover. And vertex cover of this graph is, let's see where the graph is. Vertex cover of this, this is maybe on the other side actually. Yeah, vertex cover of this graph is I need to take these 2 because I need to cover these 2 edges. And then this one is sufficient. So vertex cover is 3. Yeah, I went very quickly over those slides because there were questions about other problems.
So in
in general, it's k plus 1 if you take an arbitrary MDS code?
No. It's given by this for other. I is how many of these you have.
Like when I equal to k.
Yeah, it's n minus k over k plus k, and that is the what you get here.
Sure.
And then you can also find the matching. Now, if 2n is smaller than k, this is a little generalization of what I just said, then is smaller than I, or k in your case. K. Because in that case, you cover everything with these k nodes, because everything that remains doesn't constitute an edge, so k would be enough. So for nk, when k is smaller, when k is larger than n half, k is enough. Any other questions? So other questions that you ask in connection with this problem are the following. I wanted to talk about one of them for a simplification of what I have here during our lightning session. So I may have said that to some people in the audience during the breaks, but it's the following. Suppose I give you that lambda bits, some number of users, say you have a city, and some people want B movie and some people A movie, but there is some a fixed number of people in the city or in Berkeley students. So you know that the sum is smaller than something, and B requests are smaller than something, and alpha requests, A requests are smaller than something. How would you design a code? Now that depends on the field, not only code, but a storage scheme, which can include. So for example, if it's a binary field, you can ask how many times should you repeat alpha, how many times the other basis vector, and how many times this. Other than that, you can take all points in the projective space and ask how many times would you repeat each one, right? And you can make even this simpler. Let's say that you don't have these third constraints. You just want to cover this point and this point with the minimum number of nodes, right? How many would you? This is like asking how many, with codes for availability, what would be the, yeah. And then you can fix the field, ask how many nodes you have. So that's one. Or you can fix the nodes and ask which field, for example, you have. Something like that. So we have some results for this, but we don't have any generalization, anything. So there are quite a few problems here that are completely open. Another one is this. As I said, over the years, we kind of sporadically looked into these things. But at some point, we were at ICERM, and there was Gretchen and Sarah Anderson is her students. There were some other people there that we a little bit worked together. And we were just playing with particular examples. And Gretchen and her group, they came up with this scheme, A plus B, A plus alpha B, and then 3 A's and 3 B's. And this storage scheme became better than all of this. So if I have 8 nodes and I want to service requests for A and B, if I make A 4 times and B 4 times, I get this square. If I have these two Solomon codes from the coding theory point of view, the same thing. Well, you know, almost, right? But from service, they're different. The one here has this simplex, this triangle, and the other here has a little bit better service rate region. And for a while, we believed that coding, that it's always better to have replication, and that coding would just handle this kind of skews, this kind of extreme cases, until they came up with this red curve, which actually is the largest region. Now, having more replication is not good, because you would end up in the green one. And usually this when they're both high demands, is not something that you are interested in. And a third set of problems, and that's actually problems that we started with, is if I give you a scheme, what is the performance in terms of what is the expected time if you're a person dealing with stragglers? You can also ask how many requests are covered. So what I did here is generated by using Gaussian distribution, trying to approximate that Poisson. I forgot actually what exactly I was doing there, why I chose 4, 4, and 8, 8. And I generated this blue cloud and a green cloud. Here, blue and green, the popularity just switches from one to the other, from A to B. And then I considered several systems and a group, several codes, but one was for a system that had only 3 servers and the other for a system that had 4 servers. And I wanted to compare them fairly. I mean, you can compare them on various grounds, but service capacity or the total bandwidth was 3 times 8 and 4 times 6, so identical for both. And for this one with 3, I had codes AAB, ABB, and ABA plus B on 3 servers. For 4 servers, I had replication and I have MDS. And then I looked how many of these points, I mean, you can integrate, are out of the service region, right? So see here, service region is super simple to find, but how many of these points are out of the region? And it turns out that these AAB and ABB, they cover about 70%, a little bit more. And then AAB and A plus B covers much more, right? 87%. And then replication is better than that. So it pays off to have more servers. And then the MDS here is very good, but it would be even better, maybe some combination with replication, etc.
What is mu here?
Bandwidth. So how do I get 15? For this one, I get 6, and then the other 18 I split in 3s. So then I get 15 users. I can serve 15 when there is no of A's when there is no B. And actually, we were looking with the number. So let me just show my last slide. With the number of people that we worked, especially with the Gala, not with Gala, with Gauri. Is she here? Yes, Gauri. They're alphabetically. And Swanan Kade, who is also a Texas A&M student. We were looking into finding, if you have a code, finding how queues perform. And then we realized it's super hard. And then we said, can we at least say how stable these queues are? And so these service regions are stability regions for queues. And so that's how we started. And then some people here are some students who were visiting my lab. Some are from that ICERN program, that was a program for women. And then there is even a systems person, Gala Yadgar, who is Aitan's colleague, who is looking at how we could implement some of these. And we actually got lots of interest from industry for some reason. I guess they want to see how to code and put data in Edge and things like that. And then there is a group of mathematicians here, and the funding credits. And again, thanks to the organizers and the audience for being this active on Friday morning.
Thank you, Emina. Another question?
Is it possible to combine 2 codes also, in the sense that there was one part with one code and another part with another code, kind of, and then get some performance which kind of gives the advantage of both codes?
Yeah, I think it may be a good idea, especially because of this, as we heard earlier in the week, code combining is a natural thing, right? But it's not something we tried. And in fact, we haven't tried very many things. We just started. So almost anything you think of is probably makes sense. But this in particular, you're an expert. So, okay.
So again, like when we were working on this partial straggler problem, this idea of sub-packetization is natural. So would you gain by, let's say, calling A and B symbols to be A1, B1, A to B2, and try to, yeah.
So absolutely, you can store more on, and if you look at these, there are similarities, for example, for batch codes, and the most basic batch codes are, I don't know if these are called or something else, but you would put just one symbol per but you can have multiple symbols. And here we are subdividing the bandwidth, not the data. Subdividing the data, I would expect also would improve. But we were talking with Alex Princeton about some of these things. And one has to really understand what is data, what is bandwidth, kind of. So one has to be careful, but definitely, yeah, subpacketization should be.
All right, thank you, Emina.
Yeah, so you've got a facet description reasonably well, and you've got a volume description. Have you tried getting a vertex description of these polytopes, or saying anything about their?
Yes, in fact, when k is smaller than larger than 2n. That's why I actually mentioned both description. So for this type of things, we can describe vertices. For the other, but how that generalizes, I don't know. Maybe for other, the only other thing, another family of codes that we know are simplex. And for simplex, these graphs, it does not, here I had this greedy theorem. It does not matter if I consider only greedy matching. For simplex, it does not matter if I consider larger groups than 2. The graph turns out to be bipartite, and their matching is very easy. So yes, I cannot even predict for which ones things would be better with vertices or better with planes, or of how these graphs would look like.
All right, thank you, Emina.